which is around adaptive sample size re-estimation. Okay, so this is what most of the people love to do these days. Okay, you see in the previous group sequential design, you could only stop the study early, yeah, but you couldn't change the sample size. Okay, now we want to be able to change the sample size because let's say we don't have some information or we get new information from the study. So how do we do that? Okay, so the sample size calculation is usually based on parameters that you don't know. So let us say that initially you estimate that your standard deviation. So what are the 4 things that you need to calculate the sample size? There are 4 things you need to calculate the sample size. So can somebody type that in the chat window? All the sample size calculations require 4 things. What are the 4 things? Very good. So Mona says effect size, precision, level of significance. Very good, right? Ravi says the same thing. You want your Z alpha. So basically you want your alpha, your beta, that's your level of significance. Your effect size is the minimum in clinical difference, I guess, MCID, and precision is your standard deviation, correct? So these are the 4 things you need. Okay. Now let us say, obviously you don't know what your effect size is, correct? Because your effect size is what you hypothesize. Okay, you say that my drug can, defeat, can be better than, the existing drug by 10 millimeters of Hg. Okay, whatever, right? So your effect size is what you hypothesize. Okay, but to calculate the sample size, you also need standard deviation, which you really don't know. Yeah. So let us say that you assume that your standard deviation is 1. Okay, and basis that, this is your sample size that gives you 90% power. Okay, this sample size right here. All right. Unfortunately, let us say that your true standard deviation was not 1 but 1.4. Okay, so now what happens to your power? It drops. Correct, because if your standard deviation is more, then the power is less. Because your precision is low, therefore your power is also low, right? So from 90% power, you have dropped to 64% power. Okay. So obviously that's not good, right? Now you have estimated the standard deviation based on previous studies. Yeah. So in this case, one of the things you could do is you could say, you know what, at the interim analysis, okay, I don't want to look at the effect difference. Okay. So I don't want to find out what is the difference between treatment A and treatment B. Okay. But I'm assuming that both treatment A and treatment B are the same from a standard deviation standpoint. So therefore, in a blinded manner, okay, so I'm not unblinding the treatment arms, but in a blinded manner, I want to find out what is the correct standard deviation. Okay. So let us say that you do this at the interim analysis in a blinded manner, and you figure out the true standard deviation is 1.4 and not 1. Yeah. So what should you be able to do? You should now be able to increase the sample size to be able to get the same 90% power. Yes, makes sense? So you've not looked at the data from an unblinding perspective. So you don't know whether treatment A or treatment B is better still. All you've done is looked at the standard deviation and said, I'm going to increase that. Okay, based on that, I'm going to increase the sample size. Okay, so that is called blinded sample size re-estimation. Okay, the other kind is called an unblinded sample size re-estimation. So here, you're not looking only at the standard deviation, but you're also looking at the treatment effect. So let us say that you have done a sample size based on a hypothesized treatment effects. Let's say that's 5. Okay, the treatment effect between treatment A and B is 5. Okay, But now when you're actually looking at the data, you find out it's only 3. Okay, so you want to say, my treatment effect is small, therefore my power is also going to be low. So let me increase my sample size so that I can, so clinically meaningful difference is still okay. 3 is still clinically meaningful. But you thought your drug was fantastic, so you thought it was 5. Okay, now you find out it is 3, which is still clinically meaningful. So you say, I still want to be able to sell the drug even if the difference is 3. But to be able to get a successful study, I need to increase the sample size. Yeah. So how do I do that? Okay. Now imagine in this case, what you're doing is you're looking at the data at the interim, right? And you're going to look at the data at the end. So you're looking at the data twice. So what happens? Because you look at the data twice, your type 1 error increases. Now, because your type 1 error increases, you have to do all the things we learned before, combination test, other kinds of things to make sure that the overall type 1 error remains at alpha. Okay, so we'll see how to do that. Okay, the blinded part is easier to do. Yeah. So I'm not going to worry too much about the blinded part. That's simple enough. Let's look at how do we do the unblinded sample size re-estimation. Okay. Now, what we are going to do is only going to fix the statistical part. Okay. There are lots of other problems. Okay. So for example, when you're going to look at the data and then increase your sample size, now everybody will know that the data is not as you expected it to be at the beginning, correct? Which is the reason you're increasing the sample size. So that could result in operational biases. Yeah, and that cannot be solved by this. We cannot solve that. There is no way to take care of that. We can only test at the end to find out if the kinds of data we got before the adaptation and after the adaptation, if the data is consistent. That's all we can do. We cannot get rid of the operational bias. Okay. But by looking at the data twice, there is a type 1 error inflation, and we can fix the type 1 error inflation. That's the reason this unblinded sample size re-estimation is really not done very often, because the health authorities don't like it. However, recently, for example, for COVID, we have done a lot of these. Why? Because when you're doing, for COVID, you really needed the studies to be done as quickly as possible. So you couldn't do one proof of concept study, one pilot study, then one final study. You couldn't do all of those things because you had to get the medicines out as quickly as possible. So when we did a lot of these COVID studies, we did a lot of this unblinded sample size re-estimation, and the health authorities were okay with that. Yeah, because of the particular nature of the current situation. Okay, so the unblinded sample size re-estimation is not an easy thing to do, and it's not very commonly done either. All right, but having said that, let's take a look at how it is, because statistically it's very, very cool. All right, so let's look at how we do this. Okay, so under the null hypothesis, let delta be equal to 0. Okay, your treatment effect is 0. All right. And D is a study where you have N1 patients at interim and N2 at final. Okay. So N1 is 100, N2 is 200. So the incremental is how much? N2 tilde 100. Okay. So you start with 100 or 100, 250. So the incremental is 150. Okay. And you have a formula for N2. Yeah, which is 4 sigma square Z alpha plus Z beta over delta 1 squared, and N2 is typically N1 plus N2 tilde, which is the incremental. Okay. So for stage 1, Z1 is simply delta 1 hat over the standard error. For stage 2, for the incremental N2 tilde, Z2 tilde is simply delta 2 hat tilde over the standard error. Okay. And we know both of these are wall statistics. Okay. So we know that both these are normally distributed. Okay. No problem there. Yeah. The problem happens because based on what you're seeing at the interim, instead of N2, you change it to N2 star. Okay, and the incremental now becomes N2 tilde star. Okay, so instead of you started off with 250 patients as N2, okay, total. Now you're saying that your total N2 is 300. Okay, so your incremental after the looking at the first 100 now becomes 200 instead of 150. Okay, so now it gives you two new test statistics, Z2 star and Z2 tilde star. Okay, if you directly use Z2 star at the end, like you were using Z2 before, okay, for the total. If you directly use Z2 star, then it results in an inflation of type 1 error. We know this, right? Because we have changed the design based on what we saw at the interim. Okay, we went from N2 to N2 star. So therefore, Z2 star now is, if you use directly Z2 star as a conventional wall statistic, it will be greater than alpha. So it will inflate your type 1 error. Okay. So now what to do? So CHW, okay, Chui, Hung, and Wong. What did they show? They showed that instead of looking at Z2 star, okay, how would you do Z2 star? Z2 star would be N1 over N2 star, okay, plus N2 tilde star over N2 star. Okay, that would be the original Z2 star. But instead of that, if we changed it slightly, okay, and instead of N2 star, we actually used N2. Instead of N2 tilde star, we actually used N2. Instead of N2 star, we actually used N2. So we use the same weights as before. The only thing we changed was this test statistic, Z2. Normally we would have used Z2 tilde. Now we are using Z2 tilde star. If we use this, then this new test statistic controls the type 1 error. Okay, that is what they have shown. Okay, but there is a problem with using this, and the problem is that N2 tilde over N2 no, is much smaller than N2 tilde star over N2 star, right? In our example, what had happened? What was N2 tilde over N2? This was 150 over 250, correct? But now we increase both by 50. So now this is 200 by 300, okay, which is higher. And therefore, this formula downweights what happens in the second half of the study. Okay, so it gives less weight to the second half, which is not what you want. The reason why you're increasing the sample size is because you want to get more information. But by giving less weight, you're reducing the information. Okay, so therefore, this doesn't work well. Okay, so CHW is not very optimal because of that. All right. So CDL, Chen, Demetz, and Lan, what did they show? They showed that under certain constraints, if your conditional power is greater than some value, in this case, if your conditional power is greater than 0.5, then you can actually increase N2 to N2 tilde star without any inflation of the type 1 error. Okay, so they showed this. Yeah, this is what was shown. So using this now, we have a new set of designs, which we call the promising zone designs, which were first put up by Gao, War, and Mehta in 2008. There is a recent updated version of this from 2018. Yeah, and in this design, what they do is that they say that in certain considerations, if your data from the interim analysis is in a particular zone called the promising zone, then you can increase your sample size without worrying about inflation of type 1 error. Okay, so how does that work? Okay, and this is how this whole design works. Okay, this blue line that you see is the n value. Okay, increase in the sample size. Okay, this line that you see here is your conditional power. Okay, and what it says, this black, x-axis is your conditional power. And what it says is if your conditional power is very low, let's say less than 0.36 or 0.37, okay, then it doesn't matter even if you double your sample size. Okay, it won't matter. You will still not be able to get a positive result at the end. Okay, therefore, this zone is called the unfavorable zone. Okay, and in this zone, you don't even bother changing your sample size. Okay, you could actually stop in this zone and just declare futility if you wanted. Okay, now when you get to beyond 0.36 up to 0.9, okay, this is your interim conditional power, right? And conditional power based on your interim data. In this zone, this is called the promising zone between 0.37 and 0.9. And in this zone, you can actually increase your sample size and get some benefit. Okay, by how much can you increase? This is your percentage increase. So you can increase by 100%, which means you can double. So if you initially thought about 200 patients in your study, you can go up to 400. Okay, so between 0.36 to about 0.6162, you can actually double your sample size and you will be able to maintain your conditional power, which means that you will be able to have a much higher chance of your trial, of your study being successful. Beyond 0.6, you actually don't need to double. You can actually reduce it only by this, sort of linear trend. Okay, it's actually not linear, it's a little curve. Okay, but you can reduce it only by this much and you'll be fine. Now, obviously, if your interim conditional power is already greater than 0.9, that means your trial is already, well on its way to be successful, correct? So obviously at that point, there is no point in increasing your sample size. So beyond this, you don't need to increase. So if you're already a conditional power is 0.9 and higher, you don't need to increase. This is already the favorable zone. If it is less than 0.36, you're in the unfavorable zone, so don't bother. If it is between these two values, you're in the promising zone, so you can actually increase your sample size. Okay, and this approach will allow you to preserve your type 1 error, at the same time increase your sample size. Okay, all right, so I want to take a quick example and just show you how this works. Okay, all right, and here is what happens. Okay, this is your power conditional on your interim outcome for a fixed design and an adaptive design. Okay, and this is your expected sample size. Okay, so if it was a fixed design and these are your delta values, 1.6 on up to 2. Okay, for a fixed design, okay, it is always 442. Okay, for an adaptive design, if it is in the unfavorable zone, then it's 442 because you're not increasing your sample size. If it is a favorable zone, it is 442, you're not increasing. But if it is in the promising zone, then you increase 687, 685, 682, 679, and so on. Okay, but look at the power now. For a fixed design, if you were in the promising zone, your power would only be 62 to 77. Whereas by using your adaptive design, you can actually increase your power from 82 to 92, between 82 to 92. So you can have more than 80% power. Okay, and this is the power of, this is the beauty of using these adaptive, sample size re-estimation designs, because you can actually increase your power while at the same time keeping your preserving your type 1 error. Okay, good. All right, so I think that's all that I wanted to speak about from a sample size re-estimation standpoint.